All right, so we're going to skip ahead a little bit and talk about the big three things that are in every electrical circuit. And that is current, resistance, and voltage. Okay? So current is, most material has free electrons. And they are free to move between atoms. Okay? And when electrons move, this creates current. Okay? When it moves, it creates current. So this is defined as the flow of not just charge, but what? Since we're making a flow of electrons, what are we using? What is my current supposed to be charged as? Positive or negative?
Negative?
It should be a negatively charged. So current flows from negative to positive, and it is defined as the flow of a negative charge. Okay? Since current flows with electrons, that means it's a negative charge. So electrons like to move, okay? We have things like, I don't know if y'all remember back in elementary, middle school, high school science. But electrons, they like to have these little orbital shells. Here's where your protons and neutrons. I'll just put the N for nucleus there. Okay. So what do most atoms want to maintain being a happy atom? Y'all remember that term? In order to become a happy atom, most atoms want to have 8 electrons in this outermost ring. And that is supposed to be one of the best insulators out there. Okay? Supposed to want 8 electrons in that outermost ring. Okay? So with water, basic water, purified water, what you should see is you have oxygen atoms and you have 2 hydrogen atoms. Hydrogen has 1 electron apiece, so when they attach to that oxygen atom, they end up with 8. They end up sharing 8 atoms in that outermost ring. So technically, water should not conduct as well as it does. What allows water to conduct so well is the fact that almost every drop of water in this world is not purified. What do I mean by that? Well, it is not purely hydrogen and oxygen. If you ever read the bottle label on your bottle of water, what does it generally say?
Purified or distilled?
It says purified or distilled, but they also add minerals back in to create a taste to the water. So while they've purified the absolute heck out of it, it still has minerals and dissolved things in it that give water some form of taste. What is the best type of water to conduct? That allows for conduction. The answer to that is ocean water. Salt water conducts really, really well. So an unfortunate thing about it is the fact that salt water really conducts some of the best ways you can get it. Okay. So metals conduct really well. When we talk about insulators, what is the first thing that typically comes to mind when you think about what an insulator is? There's one common one that just about everybody considers when they start looking at insulators.
Plastic.
Not so much plastic.
Rubber.
Rubber. That is what most people consider one of the
Rubber,
best
yeah.
insulators, is rubber. Now, what if I was to tell you that rubber actually can conduct if you put it in under the right conditions? And that is actually true. There, I don't know how many of you have ever heard of the electric eel from South America. It's one of the animals in the world, one of the few, that can actually produce electricity in its own body. And the whole purpose of that is to make it to where it can't be eaten. If something like a caiman chomps down on one of these, it can put out enough voltage and current from this little animal that's of an eel, and it can actually kill something as big as a caiman. Okay? It is a just about strictly South American animal, but it is able to produce enough voltage and current. It can kill a basically the relative of the alligator. So there are people that actually go and start messing with these things, but the way you do that is generally to use very thick rubber gloves. If you ever watch any of this on TV, one of the things you'll see is they want to make sure that those gloves are dry, because otherwise having the water inside those gloves can allow for electricity to conduct through that rubber glove. Okay? This is something that happens all the time. It's something that you have to be aware of and you have to plan for, so that nobody ends up hurt by something like that. So we use a lot of cotton, I'm sorry, let me back up. They used to use cotton, wood, and paper to create insulators. What do we use today? We tend to use plastic and we tend to use silica. We don't use dry cotton, wood, or paper because while it doesn't conduct very well, it is very flammable. I'll put it to you that way. We don't want flammable around these wires, because if they decide to go off, that just basically creates tinder for whatever fire you're trying to create. So most of the time we find these things wrapped in plastic that is a blend of plastic, and I believe it's also got silica in it, which if you don't know what silica is, that is sand, or the very basics of glass. They don't conduct very well. So what you're looking at with insulators is you want something that is going to prevent the ability for electrons to jump. And you want something that will be able to withstand heat, because the worst thing about conducting any kind of electricity is it will throw off heat like crazy. Too much heat can make certain materials combust. Should they combust, then you end up in an even bigger problem and in bigger trouble. So a lot of the things that are out there, people use plastic and they use silica. Okay. Okay. All right. Any questions on any of that? We'll keep moving. I don't know why that's on there. All right, so current. Current is what? What have we said current is? Current is the flow of electricity. Very good. All right, current is the flow of the electrons. So it is, the way we calculate it is charge divided by time. The measure is in amps or amperes, depending on who you're talking to. 1 ampere is equal to 1 coulomb, which we talked about just a minute ago. It's that 6.25 times 10 to the 18th. And that is electrons flowing past a point in 1 second. Okay? So this is symbolized mathematically with an A. I'm sorry. It is symbolized as its unit as a big A. Mathematically, when we're trying to calculate for current, we symbolize it with an I. No, I don't know why it uses an I, but it does, and that is just how that goes. Okay? So electrically it's symbolized by an A, mathematically it's symbolized by an I. Y'all got any questions on this? All right. Then we have resistance, and these are a couple of different ways you can write this, but this is defined as the opposition to flow. So if we're looking at something like a river, all right, so I'm going to do kind of like a winding river here. So flow is the movement of the river downstream, yeah?
Yes, ma'am.
All right, so what stops the flow of a river?
A dam.
A dam is what stops the flow of a river. Okay? You put a dam across the river, you stop up the river. You still have some flow downstream, but the flow is less. Does that make sense? So you have your current, which is the flow, and you have your resistance, which is a dam across the river. So we measure in what's called ohms, which is represented by the Greek letter omega. Again, I don't ever ask anybody to draw this perfectly because Lord knows it's probably one of the harder symbols to try and draw perfectly. If you're having to draw the letter omega neatly as you can is pretty much what you have to do with this. It's one of the more awkward ways of writing that. Okay. But 1 ohm of resistance exists when there is 1 amp of current and in a material with 1 volt applied across. Okay. The unit is symbolized by the omega, but the mathematically it is represented with an R. So the R is the mathematical. The omega is the symbol for what it actually is. Does that make sense? All right, I'll assume so. Let's move on. So this is a symbol for a resistor. So resistors are one of the most common things you'll see in electricity and electronics. Can anybody think of why? Because it goes back to what I just said.
They help control the flow of current.
They help control the flow of current, so it keeps everything in line. So we've talked about current, we've talked about resistance, so let's talk about voltage. So voltage is defined as the potential difference between 2 points. So in other words, going back to our river analogy, if I've got a river coming from the mountains, which, by the way, that's a really bad drawing so far. So if I've got a river flowing down from the mountain, right, and it's going to the ocean, the potential difference is what is the elevation that is driving the water to the ocean, right? Would y'all all agree with that?
Yes.
So that would be your voltage. It's what is pulling the water to the ocean. The flow of the water is the current. And then generally on most rivers these days, you've got some sort of a dam that's creating resistance so the water isn't just draining all the way down all the time. Does that make sense to everybody? All right. So voltage is the driving force that establishes the flow of current. So in other words, if I don't have some sort of push to move my water from the top of the mountain down to the ocean, I'm not going to have any flow, right? It's all going to sit and stagnate right there where it's at until something comes along and gives it a push. Does that make sense? Okay. So voltage is energy divided by charge measured by the volt and symbolized by either V, which does stand for voltage, or E, which we talked about this just a second ago. What does E stand for?
Energy?
Not quite. We talked about this in the last chapter. What it stands for is
Electron.
It stands for electromotive force. And no, I might not have spelled that completely correctly, but I think that's how that's spelled. All right, it stands for electromotive force. E is typically used by some of the older companies in things like the armed forces. V has become very common because voltage and volts and everything like that, it's just easier to remember that one little symbol, I guess. I don't actually know for sure why we only use V most of the time, but it is something probably similar to that. But one of these places you'll see the E is the things like the military. Anybody that has anything to do with the military. So sources of voltage. Now this one y'all might want to pay real close attention to, guys, because these do make great test questions. So when it comes to batteries, now batteries are very interesting because technically a battery is supposed to be, if this is one cell, you're supposed to have two cells to make a battery. Okay? That's just so y'all have that information. So, what do we do with this information? Well, it's kind of an interesting way to say this. So what we have are things like primary batteries that are one and done. These are your AA's, AAA's, C's, D's, things like that. Your watch battery. Does that make sense? So then a secondary battery is rechargeable. So what are some of the things in your area that is rechargeable?
Car battery.
Your car battery? Very much so. By the way, does anybody know what actually charges your car battery?
Alternator.
It is your alternator. Your alternator is what charges your battery. Okay? So another thing that has a secondary battery is your cell phone, tablet, and or computer. Anytime you have a battery that can be recharged, you have a secondary battery. The primary batteries, again, are the one and dones. The ones that right after you get through with them, they've died completely, you just chuck them in the trash. We also have solar cells, which run on the power of light. We have generators that are able to convert mechanical energy to electrical energy. These use electromagnetic induction. We'll talk more about that in a minute. And then we have power supplies that allow you to convert AC to DC. Allow you to convert AC power to DC power. So we'll talk about a little bit more of this as we go through. Have y'all got any questions so far? All right. All right, so Ohm's law, that is so let me put it to you this way. This is one of my favorite quotes by somebody that is a very interesting character. Now, I know all of us grew up hearing the name Thomas Edison. Yeah? Thomas Edison was said to have created the light bulb. What we have come to realize here in the last few years is Thomas Edison was not so much an inventor as he liked to buy patents. He actually bought the patent for the light bulb, and he and his team are the ones that put the patent for the incandescent light bulb and created the incandescent light bulb. Most of the work was done by, can't remember. There's quite a long list of people that actually made it. Edison was pretty much the money man behind it, put it that way. But he said, and I do quote, "If I had known Ohm's law, it would not have taken me so long to make the light bulb." I'm kind of paraphrasing him on that. Okay, so this literally is the key to all electronics, is being able to work with Ohm's law. So Ohm's law, it is the relationship between voltage, current, and resistance. So E is sometimes used as a symbol for V. So mathematically, this and this are the same thing. Mathematically. When it comes to giving your results for voltage, you need to use V. Mathematically, current is symbolized by an I. When you use it for units, you use the A. Mathematically, resistance is represented by an R, and its unit is symbolized by the ohm symbol. Now guys, as I said before, don't worry if you can't get the ohm symbol right. Most people cannot. I can't even do it right. It's one of those really hard ones to work with. Simply because that's probably one of the better ones I can do. So Ohm's law. Ohm's law is the relationship between current, voltage, and resistance. And it's the formula we use for all electrical circuits. So guys, go ahead and write down these three formulas. Go ahead and write down these three formulas. You will be using these three formulas quite frequently from now on, so you might want to go ahead and start memorizing these three formulas. All right, so V is what? What does the symbol V there stand for?
Voltage.
It stands for voltage. What does I stand for?
Ohms.
No, I stands for current.
Oh, cool. Okay.
These are the mathematical representations. I is current. R is resistance. Okay? So what this one right here, the very first one translates to is voltage is equal to current times resistance. Okay? Voltage is equal to current times resistance. This one is current is equal to voltage divided by resistance. And then resistance is equal to voltage divided by current. Does that make sense to everybody? Okay? So here's a very simple way to remember it. So if you were to cover up your current, voltage divided by resistance. If you're looking for voltage, current times resistance, and if you're looking for resistance, voltage divided by current. Does everybody see what I'm talking about?
Yes, sir.
All right, any
Yes,
questions? All right, let me do something real quick, guys. I don't know who used this last, but I'm pretty sure they didn't. They should have cleaned it up. All right, y'all want to take another break for just a minute?
Yes, ma'am.
All right, guys, so getting back to it, let's kind of walk through this first one together. So we're given the formula, V is equal to I times R. So we're looking at if the current is through the resistor is 15 milliamps, and the resistor is 1.8 kilo ohms, what is the voltage across the resistor? So let's bring those down. So we have 15 milliamps multiplied by 1.8 kilo ohms. Now let's go back to the when in doubt, write it out. So this is actually 15 times 10 to the negative 3 multiplied by 1.8 times 10 to the third. Everybody with me so far?
Yes, ma'am.
Okay. So then we'll separate this out. So we have 15 times 1.8, and we have 10 to the negative 3. What does multiply mean?
Yeah.
Plus 10 to the third. So basically this ends up being 10 to the 0 What's 15 times 1.8?
27.
27. Okay. So I end up with 27 times 10 to the 0. What's 10 to the 0 equal?
1.
10 to the 0 is 1, so I just end up with 27. 27 is multiplied by 1, it's just 27. Does it make sense, guys? So I end up with 27 volts. Does everybody see what I did? Does anybody have any questions over what I just did?
Miss Bush,
Yep.
why we did not do it with the easy way, like 15 times 1.8 and that's it?
Because that's not 15, that's 15 milli. So basically what you just did was multiplied 0.015 times 1800. That's not 1.8, that's 1,800. Does that make sense?
Yes, ma'am. So we have to change it to the real number or something, right?
Change it into a format that you make sure you understand that that's not. Okay, let me put it to you this way. The reason why we have to make sure we're careful with these is because this right here,
Yes, ma'am.
this right here has meaning. If you miss that meaning, then you are going to find yourself in a world of problems. Simply because this guy right here means that my number is times 10 to that -3, which means I'm behind the decimal. So that's why I kept telling y'all a while back, when in doubt, write it out. Because that firmly affixes in your mind that that has a meaning, that that has a purpose, if you will. Does that make sense?
Yes, ma'am. Now I understand. Yes. That's why you was explaining last time.
Yes, because it has a meaning. That's why I did this with y'all. This is probably the hardest concept to begin with, is the fact that it's not just the numbers. You have to take in the metric prefixes with them. So in this case, it's not 1.8, it's 1.8 kilo, which brings that up to this 1,800. If you just take it as 1.8, that's going to get you in trouble, because what if instead of kilo, this was mega? So then you wouldn't be dealing with 1.8 K, you'd be dealing with 1,800,000. That was a mega, right? Which would mean that I'd end up with 27 kilovolts if I did that. The prefix has a meaning. Please do not neglect your prefixes. It will come back and haunt you whenever you're trying to do these problems on a test. Okay? Everybody understand kind of where I'm going with this?
Yes.
All right. Then let's go to the next one. All right, so we're looking for current when we have voltage and resistance. So the current through a 27 kilo ohm resistor is, what is the current through a 27 kilo ohm resistor if you get 100 volts across it? So I'm going to rewrite this with my numbers. So I have I is equal to 100 divided by 27 kilo. The even easier way to write this, or there's a couple different ways you can write this, guys. So you can say 100 times 10 to the negative, I'm sorry, times 10 to the 0 power divided by 27 kilo, which is times 10 to the third. You can put it as 100 divided by 27,000. Either way you look at it, guys, you're still going to end up with something along these lines. So you can very well break it all down and just say 100 divided by 27,000, which would give me what?
$270.
270. I'm not so sure about that. Let me check. So this actually should not be 270. You're doing it a little bit backwards. So in your calculator, type in 100 divided by 27 with 30 behind it, and you should get
0.0037.
Putting it into notation, you end up with 3.7. I moved the decimal place 3 places to get behind that 3. So I've got milliamps because it's 3.7 times 10 to the negative 3. You'll see that?
Okay, I did that backwards.
Mm-hmm. I know. Believe you me, I've done it a few times myself. Okay. Everybody good? Any questions on this one, guys? All right. So let me kind of put this in a bit of perspective for y'all real quick. This is a lot of words that have meaning, but let's kind of narrow down the meaning. If voltage does not change, okay, then when current and resistance, this is how the relationship between these goes. If current goes up, resistance will go down as long as voltage remains unchanged. Does that make sense so far? Then if current goes down, resistance will go up as long as voltage remains unchanged. So that means that current and resistance are inversely proportional. Does that make sense to everybody so far? So essentially what that means is that if I set my voltage to 10 volts, if I increase my resistance, I will decrease my current. And it will apply the other way around as well. If I decrease my resistance, I will increase my current. Does that make sense?
Yes, ma'am.
So then we have the second set of rules right here, and that is where if resistance is held constant, I've got voltage on one side and current on the other. If voltage increases, current will increase as well, as long as resistance remains unchanged. However, if voltage decreases, current will decrease as well, as long as your resistance does not change. And that works the same way if your if your current is held constant instead of your resistance. What it means is that, let's put it a little bit differently. So current is inversely proportional to is inversely proportional to R. Voltage and resistance and voltage and current are directly proportional as long as the third value is held as the same. Does that make sense? All it means is that when one goes up in current, if voltage is not changed, resistance, the other one will go down. And vice versa. If you have resistance or current that remains the same, then when one goes up, the other goes up. Does that make sense? So in other words, we'll go back to the dam analogy, or the river analogy here. So here's my river. I've got my little dam across it, hold back some of the flow, right? And I've got my current coming down being pushed by my voltage. Does that make sense so far?
Yes, ma'am.
All right, so if my voltage doesn't change, the amount of water doesn't change, but my current increases for some reason, let's say somebody added a bunch of water into the system or it just rained a bunch. My push has not really changed, but my current has gotten quicker, right? If you've ever been near a river in a rainstorm, all of a sudden the waters rise and the flow is much faster. It's not so much that it has extra push, it's so much that it has extra flow. Okay, so if my current increases, in other words, the water's coming down even faster than it normally does, my resistance will decrease because my resistance can't hold back the increase in current. Does that make sense?
Yes, ma'am.
Yes.
All right, so then we're part of the public works project. Okay, so let's say I want to build a bigger dam. However, the bigger the dam, the less current, the less water will come through it, which means we might end up with dry spells down the way. Does that make sense? It means that less water will be able to flow through, less current will be able to push through my dam. Now let's say that the current out, I want it to remain the same, but I'm getting more voltage up here. That means that as my voltage will increase, my resistance will have to increase as well to maintain the same current out. If my resistance remains the same, I keep the same dam, then that means when my voltage increases, my current will increase, which pushes more flow through the dam. Does that make sense to everybody?
Yes, ma'am.
Does it make a little more sense than all the other stuff? All right, so this is the effect on current with a changing voltage if resistance is not changing. So in other words, this is a fixed resistor, but it is a variable voltage source. So anytime, guys, let me go ahead and point this out since this is part of schematics. Anytime you see this arrow on anything that is part of a schematic, it means that whatever it's attached to is variable. So this gives you a variable voltage source. In other words, I can change what voltage output I get. Does that make sense to everybody?
Yes, ma'am.
All right, so if my voltage, I start out with 6 volts here and 3 amps here. If I double that, I get 12 volts and I get 6 amps. However, so that's what happened when I increased the voltage, my current increased as well, and in direct proportion to the amount of voltage that I increased. Does that, we'll see that?
Yes, ma'am.
And then if I decrease the voltage, that means that I'm going to decrease my current, because R is unchanging. In other words, my dam is remaining the same. If I all of a sudden get an influx of water and snow melt up here, my current is going to go up quite a bit. Think about the reason why certain rivers flood right after the snow melts, right? That's a high influx of voltage, a high influx of water going down that riverbed, which means that my current gets high and excessive to the point where it's going to push even harder downstream. Best analogy I can give you on that. Then let's look at this as if I've got the ability to change my resistors. So here I've got, I think that's about 12 volts. We'll call it 12 volts, and then here we'll have 12 volts. So my voltage isn't going to change, but my resistance starts out at 10 ohms, and I've got quite a bit of current. Y'all all see that. When I increase my resistance, what happened to my current?
Go less, decrease.
My current became a lot less. My current became less because I put in a bigger resistor. Okay, And then it would happen vice versa. If I went from a 20 ohm resistor to a 10 ohm resistor, my current will increase, all because my voltage did not. Does that make sense to everybody?
Yes, ma'am.
All right, so resistance is directly proportional to voltage and inversely proportional to current. Voltage is directly proportional to both resistance and current. And current is directly proportional to voltage and inversely proportional to resistance. All this means, guys, is that resistance and voltage, if voltage is going up, resistance should go up to maintain a level current. And if voltage goes down and resistance go down, they have to do it together to maintain a viable current. However, if you're trying to change the amount of current is in the system, then you're changing the amount of resistance that goes with it. So this is just a condensing of everything I just was saying. Okay. So here's the way to prove it. So I've got my voltage on this run. I've got my current on this one. And I've got my resistance set at 10 ohms. So when my voltage goes to 10 volts, my current goes to 1. So they are in perfect proportion with each other. Okay. All right, so I'm going to let y'all work on this problem for just a minute, and then we'll go over the answer for it. Give y'all just a minute to kind of get some practice in on this. All right, so what is the current for this particular problem, guys? Anybody have any ideas?
12. It's voltage divided by resistance.
Is the voltage divided by resistance. So what you should have is 12 divided by
100
is
0.12.
So what you should have had was 120 milliamps. Why is that, guys?
Because it's 0.12, it's amps. And we change it to milliamps.
When you get 0.12, you get to move the decimal back 3, -3.
You need to put it in proper notation, yes.
120 times 10 to the -3.
So that proper notation would be where you get 120 milliamps. Correct?
Yes, ma'am.
All right. Be careful with those, guys, because again, that goes back to that has meaning. And generally, you're trying to condense that meaning down so that somebody else can know exactly what you're trying to talk about. Okay? All right. So what about this one, guys?
Five 500 milliamps.
So that's 100 divided by 200, and it should be 500 milliamps. Okay? All right, let's go to this one. Skip a couple forward. So this time you're looking for the voltage. So what is my voltage here? And you are correct, Mr. Kane. It is 500 volts. All right, 5 times 100 is 500. What about this one? Is 33 what?
Millivolts.
Not millivolts, it's just 33 volts. You need to make sure you know what you're passing, what information you're passing here. You're telling somebody it's 33 volts. If you just tell them it's 33, is that amps, volts, ohms, what? What are you trying to convey?
Okay.
That's what you gotta be careful about this with, guys, is if you're trying to convey the concept, you need to make sure you convey it in the correct way so that somebody can sit there and go, oh, so I'm dealing with 33 volts, not 33, amps. You do that, and that's generally something you want to be very careful of.
Yeah, that's it.
Because you tell somebody something is 33 milliamps or something like that, they get across that sucker. That's not going to be fun. So what about this one?
Can you return back to the one we was doing?
So this one?
Yeah. Yes, ma'am. Why we did not convert that 10 milliamps to amps and then times 33? Is gonna be the same thing? Or?
So what this would actually be is 0.01.
Oh, 0.0.
And this is
Okay.
3,300. Now the good thing you can recognize is something like milli and kilo. This is -3. This is 3. So yes, they will cancel each other out. But if you don't remember that, so let's say instead of kilo, this was giga. And giga is to the power of 9. See how that could mess you up a lot?
Yes, ma'am.
So be very, very careful doing that kind of thing, guys. Yes, these two will cancel out. Kilo and milli will cancel each other out when you're dealing with the multiplication side of this. However, if I was doing a division side of this, that'd be a totally different story.
Okay.
So that's why whenever we started the powers and roots, I said, when in doubt, write it out. So you understand that kilo has meaning, milli has meaning. All of these have a purpose, and that is to convey either a really big number or a really small number into a more compact formula, if that makes any sense.
Yes, ma'am. Thank you.
So like I said, be careful about how you're presenting some of this, because when you least expect it, something like that, you have to know what you're talking about, or else it could end up getting somebody hurt. Because there's a very big difference between 10 milliamps and 10 amps. There is a heck of a lot of difference between those. And none of those differences are very pleasant if you get stuck with them. Okay. So about this one, guys.
Four?
It is for what?
That's it. I don't know. It's like kilowatt, kilo, yeah.
Just 4 ohms.
4 ohms. Okay.
It is 4 ohms. Okay?
Yes, ma'am. Thank you.
All right. So what about this one?
One 1.46, or I'm not sure it's gonna be amps or yes, milliamps, I guess.
It won't be amps. You're looking for resistance. What's the resistance setup?
Ohms.
Okay. And you said it was what?
1.46.
That should be kilo ohms. because the number is 1463.414, so on and so forth. So it's 1,463. If you do shorten it, guys, be careful when you do, because that it should end up being 1.46 kilo ohms. And why is it kilo? Because you gotta see for yourself, it's in the thousands. Okay?
Okay.
All right. So for those of you, this is actually the symbol for micro. Which what is micro, guys?
Ten to the -6.
All right. So knowing that, let's see how y'all do on solving this one real quick, and then we'll see if y'all have any questions about solving these. All right, so what is the answer for this one, guys?
$66.
66 what?
Ohms. Ohms. Or kilo ohms. Kilo ohms.
You said it was what?
66.
Not quite.
0.66.
So if you actually do this, you put 240 divided by, and you have 5 zeros in front of that first 3. You should end up with
Yeah, this is what we did. Yeah.
72.
Oh, I did 220. Okay.
So you should have ended up with 72. I won't even do all the repetitions of it. That should have been mega ohms, excuse me.
Yeah, I did 220. That's why. Yes.
That's kind of what happens. You gotta be real careful how you enter those numbers. They will trick you. All right. Does everybody see how that happened?
Yes, ma'am.
All right. Is everybody good with this set and how to do Ohm's law? We'll cover it again on Wednesday some. I just want to go ahead and make sure y'all are kind of up to date on it now so that we can go to labs and do stuff like that on Wednesday. We will be doing on campus doing labs on Wednesday. As long as the weather stays and doesn't cause too much problems.
Okay.
So let's talk about how to measure with your meter. I don't know how many of you have already gotten your meter. It's something you need to start looking at and getting towards going to. You don't need a super expensive meter. You need something that is going to hold up fairly decently, okay? What you're looking for in a meter, it can be auto ranging, it can be manual ranging. Manual means that you turn the little dial as many times as it needs to get to the correct measurement you're looking for. Auto ranging is like this guy right here, where you just click it over and it will automatically find the correct way that it needs to measure. Now that being said, let me tell you that what you're looking for with this is you're looking for something that can read milli and micro amps. You also want to be able to read millivolts. Most of the other stuff comes fairly standard. Places you can get them, places like Harbor Freight. You can go to Northern Tool. Harbor Freight, they've got 3 locations that I'm aware of. There's one in Tuscaloosa County. There's one on Pelham, right across from Old Time Pottery. There's one place out in Birmingham. There's several places you can get these. You can even get them at Home Depot, Lowe's, places like that too. Basically any place, even Walmart carries these things, guys. So do your shopping, do what you want to do and kind of think of what do you need for what you're going to do. Okay? I am not saying go out and buy a Snap-on. I'm saying buy one that's going to hold up to what you want to do. If you're going to be doing major work with electrical, make sure it can handle all the different electrical readings you're going to need. Okay? If you're just going to do electronics or some minor stuff with this stuff, then that's what you're going to do. Most of the basic meters really don't cost that much. They'll probably they should run you less than $100, okay? If you buy the really expensive ones like Fluke or Snap-on, they will cost you more. Here's one that's a fairly decent one, $45. Okay, so go ahead and be looking at getting your first meter, guys. As to how to use it with a voltmeter, this guy is placed across what you're measuring. And this one has power on. With an ohm meter, it's exactly the same as the voltmeter, only it's powered off. And the big difference here is the ammeter. Now the ammeter is one you have to be really careful of, and I'll show you why when we get to lab. But this one is placed in circuit. In other words, it becomes part of the circuit. Power on. Like I said, we'll talk more about that on Wednesday. So here's a good drawing of it. So your ammeter is part of your circuit. So essentially, I don't know how many of y'all have gone to sporting events, but if you've ever had to go through the turnstile or the gate, it counts you, right? How many people have come in today? Well, here's this gate that's got so many people, so on and so forth. That's essentially what an ammeter does. A voltmeter goes across your component being measured, whether it's your voltage source or some sort of component in the circuit. And then lastly, your ohm meter is measuring your resistance with power not applied, power off. Okay? Does that make sense?
Yes, ma'am.
All right, and then these are just the terms y'all need to know. You might want to take a picture or something. Just, like I said, we'll go back over some of this. On Wednesday. But this is the all the stuff we've gone over today. Any questions, guys? All
No,
right,
ma'am.
so we are at the end of class, which means I'm going to